Welcome to another Project 8 Byte Crash Course. So today we'll be looking at Maclaurin series. So as always, I'll go through a little introduction, go through what is taught in Maclaurin series, as well as some of the questions, before finally going through a summary of it. There's always some general advice for Maclaurin series. Basically, it's an extension of your differentiation and integration. And so you should try to integrate and differentiate as much as possible, even if you don't know what the answer may be, because usually one derivative or integration can be worth 1 mark here or there a lot. Additionally, when you are writing your answer for Maclaurin series, it will usually be in the form of like a constant plus 3x plus 5x squared plus x cubed. But the thing is that when you are expressing your answer, there may not always be a specific number for a certain power of x. So it can be like 0 plus 3x plus 5x squared plus x cubed. But there may not actually be like a constant or an x cubed. It may just be 3x plus 5x squared. Additionally, it is in your MF26. And so there are some interesting things to keep an eye on. And so you don't have to memorize any of this because it's all in your MF26. But some important things to note is that you'll be using the second line a lot. And this second line is 1 plus x to the power n equals that expression as shown below. And the thing is that whenever you use this kind of equation, it has to be in the format of 1 plus something to the power n. So when you are using this question and expression, you can actually replace x with like x over 2 or like x squared. And so yeah, that's one way you can replace the x. And of course everything will follow suit on the right hand side. Another thing you notice is that for most of these expressions, they actually have factorials. But in the case of the series for ln 1 plus x, there actually are no factorials. And finally, if you notice and see here and there, most of these series actually follow a certain pattern. And so this is what I'll be going through in terms of the content. Mainly what is covered is that you'll learn how to find a Maclaurin series, what is a binomial series, what a validity range is, as well as manipulating Maclaurin series to get certain expressions, as well as some numerical approximations, as well as small angle approximation. And so basically, what the Maclaurin series is that it's such that you can express a function as a power series in ascending positive integral powers of x. And this can only be found if f prime exists. So if it doesn't exist, that means the entire thing will break down. And this entire series may converge to fx for only a specific range of values of x. This is called the range for the validity range, a better way to put it. And basically what this means is that you can only use the Maclaurin series as an accurate estimation within this range of values of x. Otherwise, your answer may not be as reliable. So we'll start off first with the binomial series, which is what you actually learned in secondary school. And so the usual scenario you see is that in the expression you will see that, let's say n is a positive integer, and so when you have a binomial series of like the form 1 plus x to the power n, you will have about n plus 1 terms. It will be expressed in the form 1 plus 3x plus 3x squared plus x power 3 in the case of 1 plus x all cubed. But the thing is that when you learn Maclaurin series, your n can be a negative number, and this can lead to an infinite number of terms. And this is how we can use the Maclaurin series to find the expansion for 1 plus x to the power of n. And so, and of course, the thing to keep note, if you refer to your MF26 again, is that this 1 plus x to the power n is only valid if the modulus or whatever expression x is less than 1. And so, for example, before using expression, we have to factorize to create the leading one term, such as replacing the expression as a plus x to the power minus 4 and dividing it by 8. So it will be 1 plus x over 8 to the power of minus 4 times 1 over 8 to the power of minus 4 also. So you just factorize that out. Then for fractions, you should bring up the denominator, which also makes the power negative. So in the case of tangent x, it is sin x over cosine x, but we bring it up such that it's just a cosine x to the power minus 1. So yeah, that's how you basically find some of the Maclaurin series. Another way is that when given two standard functions as a product, like fx equals e power x times sin x, finding a Maclaurin series of this expansion is just by combining these two standard series together. So you will take your 1 plus x squared over 2 factorial times x minus x power 3 over 3 factorial dot 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 dot. Now, this series is also able to include y terms. So the y value is used when x is equal to 0, and then you can use implicit differentiation. So it need not be a standard expression. It can also be something random, a random function. As long as you let x equal 0, you can somehow find the y value using the Maclaurin series also. And in the case of ln, we have to make the term inside ln 1 also. So usually what we do is that we factorize the ln and split it into 2 using a product rule. So let's say you have like ln 2 plus x. You will split that ln 2 plus x into like a ln 1 plus x over 2 plus ln 2, because we are just using the product rule for ln. And in the case of a validity range, when we are given two validity ranges, perhaps through the algebra that we use in the question, we may have to find the smaller intersection of the two ranges. In fact, we have to, because if we find something like in between, then it won't really work. And so I think also that when you do your substitution, so like replace x with x squared or like 3x, you see in the future questions, is that you will have to replace your x in the modulus also. So in the case where it's like 1 plus 3x squared to the power n, you will have a validity range of 1 over 3 to the power or 0.5 plus and minus of each other. And so we can also use the differentiation and integration of a Maclaurin series so as to find a different expression altogether. So like for example, in the case of cosine x, you have that Maclaurin series as follows. But if you actually differentiate it, you of course differentiate cosine x to get minus sine x. Then you of course differentiate the right hand side also. But the thing is that once you manipulate to get your sine x, it's actually the same as what you see in your MF26. And another thing is that when the question changes one of the x signs to negative, so you place x with like minus x, what happens is that actually you only change the even number terms in terms of their positivity, while all the odd number terms, they still have the same expression in a way. So this is a guideline for how to use implicit differentiation, because when you are using Maclaurin series, of course, I'll go back here. You see that for the first expression, fx is equal to f0 plus x f prime 0 plus x squared over 2 factorial f prime prime 0, and so on and so forth. And basically this means you have to do differentiation. And so when we are trying to do the differentiation, we may sometimes have to use implicit differentiation. And so this is just a general guide as to how to do the differentiation. If you see fractions, you can do a cross multiplication between x and y. Or in the case of like square roots and cube roots, you can take squares and cubes so as to eliminate it. Then in the case of composite functions, we can also take the inverse. So in the case of like y equals sine inverse x, we can just apply a sign to both sides, and then we get sine y equal x. So these are just some ways to make your differentiation a lot more easier to handle. Another thing is that sometimes they will ask you for the equation of the tangent. And so in this case, it's just gonna be in a case where it will be y equal ax, where a is the coefficient of the x term, because all the other terms will be 0 apart from x, which is then differentiated into a constant. And another thing is that it's impossible to obtain a Maclaurin series for ln x, because ln 0 is undefined. So this is why when we use Maclaurin series, we have it as ln 1 plus x. We cannot do it as ln x because otherwise you won't get a proper answer. And so the next part is on approximation. So some questions may ask you what you think of the approximation you do during your Maclaurin series. And so there are two ways you can improve your Maclaurin series. One is to choose an x value of a smaller magnitude, such as something which is like 3 decimal places, or something close to 0. Or you can include terms of higher powers in the Maclaurin series for fx. So you realize that actually this list is, in terms of expressing the Maclaurin series, is non-exhaustive. You can go on for however many differentiations you want until you can get something more precise. And so that's another way. Yeah. And so the best approximation is proven by showing the inequality between two terms. But it shows that one approximation is better than the other. However, this rule only works, of course, if x value lies within the validity range. Otherwise, the Maclaurin series graph and the true fx graph will actually diverge from each other. And so ultimately, the suitability of substitutability of the x value depends on the approximation. And so lastly, they may ask you for like a percentage error. And so what percentage error means is that you take your estimated value minus the actual value divided by actual times 100%. And so that's one way you can find the percentage error. Alternatively, they will ask you to integrate the Maclaurin series. So as I show here in this case. When you differentiate cosine x, you will get minus sine x. The inverse can also take place where you have the series for sine x, and then they ask you to integrate the entire thing to get cosine x. So that can work both ways as well. Yeah. So this is just an example of what I mean by finding the difference. So in one of my tutorial questions, they want you to find the set of values for which the value of Maclaurin series is within 0.5 on the value of the actual fx. So what you do is something similar to what I wrote in my GC over there. The first equation will be the actual equation. The second equation will be what I wrote in my Maclaurin series answer. Then I will take the modulus of the difference between y1 and y2. Then I take the line, or rather I create the line of I equals 0.5. And then I try to find the intersection between my third expression, y1 minus y2 modulus, and y4, y4 equals 0.5. When you find the intersection, that's when you find out that the difference is exactly 0.5. So you just find the range of values such that this difference is less than 0.5. And so yeah, that's how I came to the answer of minus 1.96 is less than x is less than 1.56. So just bear this in mind, and this is how you really find differences using your graphing calculator. And then lastly, there's this part on small angle approximation, which is also known as quadratic angle approximation, because when in doubt, you can just take parts of the sine x and cosine x series to the power of x squared. So actually sine x for smaller values of x is just approximately x, and in case of cosine x is actually equal to 1 minus x squared over 2. Likewise, tangent x by its name is just going to be the tangent, and so tangent x is also approximately x. And so also where possible, use sine over cosine as is simpler in terms of the Maclaurin series also, because it's just going to be x. And so we can use small angle approximation when the unknown is sufficiently small. And what sufficiently small means is that if the angle is about 6 degrees or like 0.1 radians or lower. So if they ever mention small angle approximation, you'll use Maclaurin series and you use the approximation that sine x is equal to x, or cosine x is equal to about 1 minus x squared over 2 factorial. And what we do is, because Maclaurin series can also make things look a lot more neat, as the square roots are removed. And so don't try factorizing any certs or anything. So in the case of small angle approximation, you can also replace x with like different values. So if you replace x with 2x, so if you want to find the small angle approximation of sine 2x, it's just basically replacing x with 2x. In the case of cosine 2x, it's just 1 minus half of 2x squared. And so we can also use the factor formula if the trigonometry is too complex and available on the MS26. And you will use the phrasing, since theta is greater than 0 and theta is small, we can therefore use the small angle approximation and therefore say our answer is as such. And so now we'll be moving on to the questions, of which I have 6 or 7 of them. And so the first part is finding the Maclaurin series of ln 1 plus cosine x. So what we're going to do is that we're going to use the standard series of ln 1 plus x. But inside the ln, we're going to replace cosine x as the substitute for x. And so we will get 1 plus 1 minus x squared over 2 plus x power 4 over 4 factorial. And so after getting this, we are going to divide the entire expression by ln 2 using product rule. And so we will get ln 2 plus 1 ln 1 minus x squared over 4 plus x take divide by 48. This second term can then be converted into a general function where fx equals ln minus x squared over 4 plus x cosec over 48. And so in the end, your y will be equal to ln 2 plus basically the expression of your MS26, which is minus x squared over 4 plus x power 4 over 48 plus this entire thing square over 2 factorial, which is something similar to what you see in your MS26. It's just that we're replacing our x with this giant x squared over 4 plus x power 4 over 48. And so if the answer is just looking for powers of 3 and below, it's just going to be ln 2 minus x squared over 4 plus dot dot dot. Then in the case of the second question, we can also use the Maclaurin series to find tangent x. So what happens is that we will turn tangent x into sine x times cosine x to the power of negative 1. We then substitute x and cosine x for their respective Maclaurin series, and we turn the series of cosine x into a new series where the power of minus 1 is of course accounted for. And so As you can see while we're working, that's basically how I did it. You put the sine x series in, you put the cosine x series in, you try and get everything out there first, then afterwards, you try and simplify your cosine x expression. And so what you do is that you just do something similar to what I say about the 1 plus x series, except that instead of x, you replace your x with minus x squared over 2 factorial plus x power 4 over 4 factorial. And so basically that's what I did. Then afterwards, you simplify it, you expand things here and there, and eventually it will simplify to get x plus x power 3 over 3 plus 2 over 15 times x to the power 5. This is a rather standard question. And so you don't necessarily need to memorize it. Although it can be useful, you don't need to memorize the Maclaurin series for tangent x, even if it isn't in your MS26. So yeah. And then likewise, if they ask for cotangent x, which is just tangent x simples, we can just take everything of tangent x and then power minus 1, and then find a new series for that. So we don't necessarily have to find like cosine x over sine x and repeat the whole process again. The next one is finding the Maclaurin series of exponentials such that e to the power of 1 plus 2x to the power 0.5. So we're just going to expand the series of 1 plus 2x to the power 5. And eventually we'll get 1 plus x minus half x squared plus half x power 3. Then we will factorize the e1 out because when you look at your Maclaurin series, what happens is that you get e to the power x, it's not e to the power of 1 plus x. So actually, what we are going to do is that we can just replace x with our entire x minus half x squared plus half x power 3, and we factorize this e out so that we can make it similar to the Maclaurin series format. Then we will convert that inside expression into the Maclaurin format series as such, and basically the final answer will be a mix and match to get e times whatever is inside, which in this case is just 1 plus x. For scenario 4, they ask you to find the Maclaurin series of e power x over 1 plus e power x. And so what we're going to do is that we're going to bring the denominator up. We have a power minus 1, but we can just use the Maclaurin series as always. So we get 1 plus x plus dot 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 times 1 plus 1 plus x plus dot dot dot. Then we will remove the 2 to the power minus 1 so that we can have our last part in the form of 1 plus half x to the power minus 1. We will then use the Maclaurin series to get into 1 minus half x plus dot dot dot. And then we just simplify everything, combine everything together. We will get half plus 1 over 4x. Then for question 5, it's actually more oriented towards small angle approximation in some way. And so they say that given theta is sufficiently small, show that tangent pi over 3 plus theta is actually approximately equal to square root 3 plus 4 theta. So actually, if you look at MF26, you realize that you can actually use an addition formula of tangent. And so what this does is that it will split up this combined expression into tangent pi over 3 plus tangent theta over 1 minus tangent pi over 3 times tangent theta. And so fortunately, we can use our GC, and we'll find out that tangent pi over 3 is actually equal to square root 3. And then for the denominator, we bring it up so it has a power minus 1. And then we realize that our tangent theta is actually approximately equal to theta also. And so after this, we do the simple expansion for Maclaurin series, and then we'll get something like square root 3 plus 3 theta plus theta, which of course will lead to our final answer. And so the key is that we can use our trigonometry addition subtraction formulas in MF26 also to break down the tangent. And although it isn't specifically x, we can use an approximation such that tangent theta is approximately equal to x. The second part is that given that y equals secant squared x, show that d squared y over dx squared is equal to 6y squared minus 4y. And so for this part, we are just going to differentiate our y equals secant squared x. You may not know how to do this question, but the least we can do is just differentiate and see what happens. And so in this case, we bring down the power 2, we have the secant x, then we differentiate the inside of secant x, which actually if you refer to your MF26, it's actually just secant x tangent x. This will simplify into 2 secant squared x tangent x, and because we want to answer in terms of y, that's why we are going to convert our secant squared x to y first. Then we differentiate the entire thing again. We will end up using product rule as well as using implicit differentiation, which is how we get another dy dx. So after that, you get everything there, and then given your tangent squared x, what you can do is that we can again use a trigo identity and convert our tangent squared x into secant squared x minus 1, which in this case is just y minus 1. You rearrange stuff here and there, simplify, and eventually you get your 6y squared minus 4y. For part 2, they say by further differentiation, find the first 3 non-zero terms of the Maclaurin series for secant squared x. And so usually when they say by further differentiation, you just keep on differentiating. Usually a word of advice is that you will usually never exceed 4 differentiations. Usually that's the maximum they give. And you can look at the mark allocation as well to see how much you might have to differentiate. But it's always just check and see how many terms you need. If you do too little, just improvise on the spot and add another differentiation beside your main answer. And so in this case, we just do the differentiation for d power 3y over dx power 3 and d power 4y over dx power 4. Then we just let x equals 0 and find the expression for y dy dx, d squared over dx squared, d cubed y over dx cubed, and d cosec y over dx 4. And in this case, we will get that. We insert the numbers into the format, and then we will get 1 plus x squared plus 2 over 3 x power 4. Notice that there's no expression for x or x power 3. And then lastly, for part 3, hence find the first 2 non-zero terms for the Maclaurin series for tangent x squared. So the thing is, we know that already from our trigonometric identities. The tangent square 2x is actually equal to secant square 2x minus 1. And so what we're going to do is we take our 1 plus 4x squared plus 32 over 3x power 4, and then we basically make tangent 2x squared the subject. And so in that case, it will just be 4x squared plus 32 over 3x power 4. And so yeah, we try to make use of trivial identities to approximate the given expression. And so we don't actually need to manually find the sine and cosine series and then manipulate everything here and there. We can just do this. Then the next one will be this question. And so we want to expand the square root of 4 plus 2x in the ascending power of x up to and including the term x power 3 and say the value of x for which this expansion is valid. Given that e power y equal 1 plus sine 3x, prove that d squared y over dx squared plus dy dx all squared minus 9e to the power minus y plus 9 is 0. By further differentiation of this result, find the Maclaurin series for y up to and including the term x3. That's the first part mainly. And so in this case, what we will do is that we will take out this 4 square root. So if I trace out 4 square root is actually equal to 2, then your inside will just be 1 plus x over 2. Then we will use the Maclaurin series, insert it in, replacing our x with x over 2, and letting our n be half. You do that, you insert everything, simplify everything, you will get 2 plus half x minus half. 1 over 16 x squared plus 1 over 64 x cubed. And for the validity range, is normally modulus of x is less than 1. In this case, because we replace our x with x over 2, in this case, we do the same replacement. And in this case, the answer will be that the validity range for which we can get a reliable estimate is going to be minus 2 is less than x, which is less than 2. And in case of part 2, it's mainly just a differentiation of the given equation. And so what happens is that for the left hand side, we will use implicit differentiation, which is how we get a dy dx. And for the right hand side, we're just going to differentiate the sine 3x to get 3 cosine 3x. Then we do it again. We will use product rule also, which is how we get e power y. Differentiate the dy dx to get d squared y over dx squared plus e power y times dy over dx times dy dx again. And that's how we get that. And then you realize that it's actually equal to minus 9 sine 3x, which is actually equal to minus 9 times e power y minus 1. And so after you get your d squared y plus dy dx minus 9 e power minus y plus 9 equals 0, you can then differentiate with respect to x once again. And that's how we get our d power 3y over dx power 3 plus the following expression. And to find the Maclaurin series, we just let x equal 0 to find out what is y, dy dx, d squared y over dx squared, and d cubed y over dx cubed. And so that's how you get the Maclaurin series. The last part asks you to find the integral of a long expression. And so what we can do is that we can again use the long product rule. So we can split this out. So we will get 2 times 1 plus x square root minus 1 plus sine 3x. And so we can first simplify the 2 times 1 plus x, put it inside, you actually get 4 plus 4x. And so then if you factorize it is 4 plus 2 times 2x. What we are trying to do is basically fit something similar to what we got in part 1. And then we try and use the Maclaurin series inside that. And so as a result, we can simplify such that our 4 plus 4x all squared now all cubed or square root minus our ln 1 plus sine 3x can be replaced as such. So the first part will just be the same as the first Maclaurin series. I'll replace x with 2x. Then the next part is just going to be the answer from our part 2. Then we take everything together, put it into a single expression in terms of ascending powers of x, and then we just integrate the 2 minus 2x plus 17 over 4x cubed x squared minus 35 over 8x cubed. Put it into our GC and we get 0.19131. And lastly, is a VJ question. And so the Maclaurin series for x is given by 1 plus x squared over 2 plus 5x power 4 over 24. And so use this above result to find the series expression for second power n 2x up to and including the term x power 4. And so what we can do is we try and visualize this expression as a binomial series. We get n choose 1, n choose 2, etc. And what happens is that after this, then for the last question, they say that the Maclaurin series for secant x is given by 1 plus x squared over 2 plus 5x power 4 over 24. Use this above result to find the series as mentioned for secant power n 2x up to and including the term x power 4. And so what we can do is actually we can visualize the expressions of our binomial series to get n choose 1, n choose 2. And so first we let our expression for secant power n 2x be as such. So it's basically that secant x expression to the power n, and then in this case we want to have 2x, so we replace x with 2x, so we get the third line. Then afterwards we want to basically replace this power n with n choose 1 plus n choose 2, so that's how we can actually do it this one way. Then afterwards, after we do this, we actually can just replace our n choose 1 with just n, then n choose 2 with just n times n minus 1 over 2. Yeah. Then like that, we can just expand everything and simplify, and then we get the constants of a equal 1, b equal 2, c equal 3, and d equal 2. Then yeah. So in the case of the last part, which is actually an approximation of the secant 10, the secant power 10 to letting s 0.2, you just insert this line, you get 1.221. So yeah, that's how you do this question. This is a rather out of the box question, but this is just another way of thinking as to how they can show these kind of questions, which is actually making more between your binomial series and your Maclaurin series a lot more also. And so these are just some extra learning points from some other questions I did. And that if, let's say, k is small, then k sin x will also be small, and k squared sin squared x is also small. And so in this case, you can in a way ignore some of these calculations also because they are rather insignificant. And then they say, there are some questions that will say verify the correctness, which means using an MS26 and using whatever they give you to match the expression you actually got in your previous part. Then Maclaurin series of a derivative as a second part of a question. And so what happens is that when you do your integration differentiation to get your different Maclaurin series, you still have to get a plus c, which you need to solve. It's only if they want a specific answer where there's an upper limit and lower limit, you don't need a c. Then in the case of sine x plus pi over 3 or cosine x minus pi over 2, you use your MF26 to use addition and subtraction formulas as well. So yeah, that's all I have for this video. Sorry if my voice was a bit bad today, but yeah, trying to recover from something. Anyway, I hope that you are able to learn something, and if not, you can always just contact me on my Telegram. All the best for your whatever you're studying, and hope to see you in the next video. Bye.